Good morning, everyone, and welcome to the next installment of the JK-MRC Friday Seminar Series that take place here in Indopili and online, and as it is the case today. My name is Karina. Myself and Katerina have the honor of organizing the seminar this year and introducing the speakers. Before we start, on behalf of the University of Queensland and the Sustainable Minerals Institute, we would like to respectfully acknowledge all traditional owners and the custodianship of the land on which we all meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connection to country. We recognize the valuable contributions to Australia and global society. Today, our speaker is Dr. Alexander Wilson from Minerva Intelligence. Dr. Alexander Wilson completed his PhD in 2019 in physical volcanology at the University of British Columbia in Canada. Alex is a geoscientist and software developer with diverse experience in academia and industry, specializing in numerical and geostatistical modeling with machine learning. Alex enjoys solving problems with creativity and innovation using Python. Alex has worked in various field mapping-based roles in iron ore in Western Australia and porphyry exploration in Canada. And he has experience in volcanology, natural hazard assessment in Natural Resource Canada. In his current role at Minerva, Alex is the technical product owner and lead data scientist creating Driver. Driver is a 3D modeling software for mineral system that was using machine learning geostatistics to model drilling data automatically. The title of our presentation today is Automatic Block Modeling Using Locally Adaptive Machine Learning. Without further ado, please help me to welcome Dr. Alex Wilson.
Okay, can you guys still hear me and see the presentation here? Awesome. Thank you very much for having me. I really appreciate it. It's always nice to give a talk to the upside down side of the world. It's getting late in the afternoon here and we're getting into winter, so it's nice and dreary and rainy outside. Yeah, so I work for a software company called Minerva Intelligence. We're a pretty small group based in Vancouver, Canada, about 20 people. And I promise I'll try and not have this as a shameless software pitch. However, some of the content you'll see is sort of aimed towards marketing and getting clients. But if you're interested in any of this, I encourage you to reach out to us afterwards. We are a fully sort of software as a service solution that can be run or sort of used on any project or product that you have. So I'm going to talk about automatic block modeling, or our attempts to go down the road of automatic numeric block modeling. In particular, trying to lean towards locally adaptive methods that don't necessarily assume global stationarity, and utilizing new or sort of novel machine learning or unsupervised machine learning techniques to support these methods. Change slide. Okay. So Driver as a software and the sort of research projects that we've been undertaking at Minerva, they started about 4 years ago. It's a relatively young software offering out there. But it all started around about sort of 4 years ago with the intention to try and do a better job understanding the multi-element geochemistry surrounding porphyry deposits. We have some wonderful porphyry deposits in British Columbia here, and many of the geologists that founded Minerva Intelligence were involved in alteration mapping, mineralization mapping, and coming from a geochemical perspective, we were particularly interested in understanding how the multi-element geochemistry can control the formation and distribution of these deposits. And so we started evolving towards a product that enabled us to very rapidly and semi-automatically create numeric estimations or interpolations using basic geostatistic techniques, and then trying to understand 3D anomaly zones within those deposits. We very quickly realized that, one of the things that holds back these kinds of studies in these often very rich and wonderful drilling data sets is just the time and effort that is usually required to make a geostatistical interpolation. In other words, to convert the sparse downhole data that we collect, which is often a multi-element or a multi-attribute point cloud. Once you desurvey and maybe composite the data, we end up with a bunch of 3D sample points under the earth. And we want to convert this into a regular grid. We want to convert this into some kind of prediction that is regularly sampled across the deposit area so that we can start interacting and interrogating that data in a full sort of 3D environment. And one of the problems, of course, is that we employ a geostatistician or a resource modeler to model the economic element, the gold, the copper, however, very commonly leave out some of those additional attributes, especially early in the sort of data collection phase. Even though it is now standard in these projects to assay for a very large multi-element geochemistry suite. We often have 30 to 40 different numeric elements or attributes sort of estimated in these systems. And they can be used for a very vast array of reasons. We can use them for geochemical vectoring, for target, resource expansion, better structural understanding of the deposit. Rock property data, they are very rarely, sort of predicted and taken all the way through into these 3D block models. And then, of course, deleterious element modeling, toxic, environmentally damaging, or potentially metallurgically penalty elements. All of this information, we believe, should and could be modeled very early on in the resource development stage, and should be modeled continually and updated through the resource development process. So this is kind of our mission, was to write software that can support this kind of holistic deposit understanding. So we ended up coming up with Driver. Driver is now developed into a fully three-dimensional web application where you can access Driver from wherever you are in the world. We went straight for writing and developing on cloud systems. So all of the processing is offloaded from your local machine. It makes it very easy. It makes it very fast. Basically, we can tap into significant computational resources. I'm talking thousands of simultaneous processing virtual machines, which enables us to run relatively heavy computational tasks in the form of exhaustive machine learning analysis on these deposit data sets. So Driver sort of has 4 components to it. And the first part of this talk, I'm going to lead you through some of these components and give you a little bit of a demonstration of the web application and how it sort of works, so you get a bit of a flavor of what I'm talking about. And then I'm going to start talking a little bit more in depth about some of the local or sort of non-stationary scenarios that some complex modeling situations come across. So there's 4 components to our system. The first is an unsupervised machine learning technique for a data-driven assessment of the directional controls in a deposit data set. And that is the anisotropy, or the understanding of changing directional trends or grade trends within the system. on an element by element basis. Your gold doesn't necessarily have to have followed the same fluid sort of pathways as things like your arsenic, your potassium, or perhaps they were controlled by different sort of different processes. We then tap into the beautiful power of Microsoft Azure virtual machines and parallelized block modeling, which makes things nice and snappy. And then I'm going to talk a little bit about zone anomaly identification, basically looking at these block models and identifying, using again a locally adaptive machine learning technique, sort of computer vision style analysis, to extract anomaly wireframes or three-dimensional sort of spatial zones in a deposit, and then start talking about how we can interact with these spatial zones and understand multi-element geochemistry or proxies for different geochemical or geological processes. So to get into that a little bit deeper, and this taps on one of the reasons that these deposits are often challenging to model, slow to model. We don't model all of the different attributes. As you can see in this driver data set here, I've got a whole bunch of different geochemical attributes to this data set. There's 10 or 15 or something like that. And our sort of vision was to be able to equally and sort of on a sort of similar platform model all of these attributes in as little time as possible. And I'll just point out, no, this is not the highest, most accurate geostatistical method that you will ever see out there. There's certainly lots and lots of nuance to modeling these data. And our goal has never been to produce the most accurate geostatistical method out there. However, for a deposit understanding, an exploratory mindset, this system provides really reasonable and adequate rapid results. So the first hurdle to come across is to understand anisotropy in the data. And as I mentioned, each of these attributes could be controlled by a different process, so they can each have a different anisotropy. Anisotropy is often represented as this little M&M shaped ellipsoid, which is a three-dimensional ellipsoid that's elongate along three principal axes. And the ratio of those axes tells you how biased the particular attribute is in a certain direction. And this is critical for geological systems. Our deposits often follow planes, or lineaments or folds or structural planes, lithological planes or sort of stratigraphy. And so anisotropy is sort of a critical component to being able to automatically nail down and understand for each of these systems. So we use an algorithm that we have developed called spherical continuity mapping. And it does exactly what it says. It uses a spherical space and it is able to map continuity in every direction simultaneously. And we end up producing this little stereo net, which is a spherical plot that gives us this quantitative sort of exhaustively sampled heat map of relative directional continuity. And from that, we can back calculate and fit an ellipsoid model, which consists of three principal axes that have relative ratios. So you can see the major axis in this deposit here was fitted along this sort of 45-degree shallow trend. Semi-major is orthogonal to that. And then the minor is the third sort of near vertical axis in this particular stereo net space. I'm going to talk about this more later on, so I don't want to get into it in too much detail right now. But this algorithm can also be applied directly onto this drilling data set, no wireframing necessary, to understand three-dimensional and locally varying anisotropy configurations. So instead of giving it, and I'll talk more later, so don't worry, but instead of giving it the entire global data set, we give it lots and lots of overlapping little moving windows, subsets of data, and then the algorithm can be run on each of those subsets in turn, and we can back calculate this ellipsoid field. This is something that, if you're familiar with some geostatistical modeling solutions out there, they do offer this functionality. However, defining this ellipsoid field has always been a manual process or an interpretation-driven process. As far as I know, this is one of the first fully data-driven, unsupervised methods that develops this ellipsoid field on its own, directly from the data attribute itself. Just a teeny bit more information about that spherical continuity method. It's directionality analysis that is not based on a variogram, and that's part of its beauty and its power. Variograms are an indispensable tool. However, they are subject to sample binning. They're subject to grouping of different lag groups and therefore binning, and therefore they're extremely subject to outlier data, which makes using a variogram to determine directions of or grade trends in your deposit, it's a kind of a poor tool for that. This method, in contrary, takes in three-dimensional data with a measured numeric attribute. In this case, we're looking at a set of sort of dipping planes in this deposit here. It takes this information in, it runs this spherical continuity mapping algorithm, which basically is analogous to standing at, many different points in the data, looking in all three directions, and then recovering the strength of attribute continuity, or how continuous is that attribute in a certain direction. We end up providing the user with this nice colorful stereo net that gives us a representation of 3D structure in the deposit. In this case, you can see that we have a dipping plane that is starting to appear from the stereo net, and we're able to automatically pick out the principal axes from this stereo net here. And so we pick the hotspot for the major axis, the semi-major and the minor axis. That gives us an appropriate ellipsoid that is representative of a grade trend in 3D. And then from that, we can start doing our oriented variogram analysis. So this kind of flips the traditional process a little bit on its head. This algorithm comes and does this work for you, where you come in and try and understand directional trends. This does this automatically, and then we can start running the variogram analysis. But the key here is we have a lot less number of possibilities, so things are a little bit faster and easier to sort of automatically optimize. So once we have gone through the painful geostatistics process to understand directional trends in the data, and we're now armed with variogram models that represent the attribute behavior with space and direction, we can now plug these into standard interpolation algorithms. We deal with inverse distance or ordinary kriging in this case. We can plug these into these algorithms and make a numeric prediction of grade across the deposit area. Basically take that sparse data and accurately and reasonably interpolate it into a three-dimensional block model. And that creates the basis of the data set that we then will use to start interrogating it for a multi-element geochemical space. I'll just skip this. A pitch driver can work with any geological domain sort of structure that you have. So any of these algorithms can be run within subset domains or any geostatistical domains you might have previously outlined. If you've got fault blocks or sort of mineralization centers, we've worked hard to make sure that this software can deal with that with the nuances of those geological configurations. So now getting on to the fun stuff of recognizing three-dimensional shapes and features from this data automatically. The immediate problem that we had once we started generating tens and tens of different attribute block models, we had block models for 32 different attributes in each data set that we were working on. The immediate challenge is, how do you interrogate these data in some kind of reasonable way in the form of understanding where the geochemical anomalies lie in those data sets. It's very, very hard for a human to look at a 40-layer deep block model and start evaluating where highs and lows are in a 3D spatial sense. So the next sort of locally adaptive algorithm that we have developed is sort of a combination of spatial statistics and unsupervised learning again. And what this does is it takes a block model like this one here, where I've got a sort of high-grade gold zone in the core of this deposit. It takes this block model and it looks at each block individually and then says, I'm a block and I'm surrounded by a local neighborhood of other blocks. How does my value or my grade compare to my local neighborhood? And am I considered in the local sense, am I considered to be an outlier? Am I different from my local neighborhood, or am I similar to my local neighborhood? And from that, what we can do is we can basically segregate or divide the blocks down into groups that tell us whether a block is considered to be a high value that is surrounded by other high values. And then we can combine them all together, and we end up with a really neat representation. It's just a hypothesis, but it is a local clustering method that gives us a cluster of blocks that are representative of an automatically generated zone anomaly. In this case, it works pretty intuitively. We have low values around here, we have high values in the core. This method, or sort of this combined algorithm, is basically able to automatically decide where it should draw wireframe boundaries around this sort of grade center. And it's really flexible. It's really neat because this is not subject to a human going in and supplying a cutoff grade or some kind of static sort of threshold. So if I'm dealing with gold, it's easy. I can come in and say, hey, I'm interested in gold that's, greater than 0.3 grams or something like that. But if I'm dealing with selenium or, rubidium or phosphorus or nickel, I don't necessarily know what is considered to be important or what's considered to be anomalous in this data set. I'm unfamiliar with those elements and how they're behaving in this sort of setup. They're not the key commodity elements of interest. And so this is a method that is it basically doesn't rely on a human's understanding of what is considered significant or not considered significant for each attribute. It's able to look at the data in turn. It's able to decide that within this data set, this block model, these portions in 3D are considered to be locally anomalous. And of course, it's static and it's applied to all of the different, it's not static, it's flexible and it's applied to all of the different attributes in turn in a reasonably consistent way. I'm going to show you more about that in a couple of minutes. And finally, we get to the overall goal of what Driver was designed for, which is to understand the deposit through a spatial overlap scenario, a multi-element geochemical overlap sort of configuration. And that's the heart of the system that we've built. It's a means to an end to get you to a point where you can create these three-dimensional block models and then evaluate them in a fully sort of interrogative, interactive space to create, to your heart's content, any number of multi-element geochemistry proxies that might be important for your particular study. So if you're looking in a porphyry system and you're looking at potassic alteration, you might come in and start overlapping the anomaly zones that were generated for the key ingredients that speak to you representing potassic alteration. Perhaps a potassium ion, magnetic susceptibility, gold and copper mineralization assemblage, and we can generate that overlap for you sort of nearly instantaneously. Live demo number 1. Okay. So I'm not going to spend too much time here, but this is the driver web app. It's accessed, you can access it wherever you are in the world, and it's a software as a service solution. So you can come in here and upload, your drilling data. You can create projects, download things, modify everything, and schedule any kind of processing that you're interested in. In this case here, we're looking at a very small, neat porphyry copper gold deposit located up in northern British Columbia. It's a sort of relatively modern data set. I think there's 45 different drill holes here. And it's based around a pencil-shaped porphyry intrusion that has been truncated along its base by a thrust fault. So we have a nice little 3D window where you can interrogate this information. But what we're interested in is some of the block models and some of the results. So here I'm looking at the concentration of gold, and we can set off our anisotropy algorithm. I'm just going to run this in a global sense, assume sort of geometric stationarity in this deposit in the first instance. And what this will do is it evaluates the directional continuity within the gold attributes. It provides us with this 3-dimensional stereo net here, which gives us basically a model of the anisotropy ellipsoid and the principal 3-dimensional principal axes that represent directional continuity in that particular attribute. And so this is just run on gold. It's only looked at gold. It hasn't looked at any of the other attributes under this particular object. Once we've got that direction, we can evaluate a variogram oriented down that direction, and then fit simple variogram structures to come up with a variogram model. And a user sometimes wants to come in here and sort of make things a little bit more complex. Add nested structures, perform normal score transformations or other sort of manipulations on that. The really neat thing, though, is when you start comparing and looking at the directional results for different attributes and how they all performed. So this is gold, but we could also take a quick look at copper. Gold and copper are very sort of closely correlated in this system. They're both mineralization elements in this deposit here. And so I can look at the gold and the copper stereo nets, and I can just flick between them. And kind of subtly, you can see that they're slightly different, but basically the two independent analyses have provided nearly identical results. So this is an independent way of sort of assessing the directional continuity of the attributes. They don't necessarily have the same variogram or variogram model, but they both appear to have very similar ellipsoid or anisotropy parameters. If I look at an attribute that's not necessarily controlled by that mineralization direction, and I like to show bismuth because it's a nice sort of scattered, irregular attribute that doesn't really show any kind of directional trend in this configuration whatsoever. We have sort of slightly high bismuth values that appear to be nearly erratic occurring across this deposit. There's a slight elevation of bismuth up in this upper area, which is probably a lithological contact. But if I look at the bismuth stereo net, it's very, very different. The business stereonet is basically saying that, hey, we don't have a really strong football-shaped anisotropy in the distribution of bismuth in this system. And I can throw the bismuth ellipsoid into the 3D window. And even though this is a red to blue color map, this is nearly an isotropic result. So the automatic machine learning is basically telling you, hey, don't try and impose a strong anisotropy on your bismuth block modeling, on your estimation for bismuth, because bismuth doesn't show a strong directional trend. So we can quite easily flick between all of these different attributes and really form a rich picture just quite quickly of how the different elements are maybe necessarily correlated with each other in their sort of directional controls. It's quite an interesting way of, it's a new and sort of interesting way of analyzing things. One of the really neat side effects of this automatic routine is that it really opens us up for experimentation, and it opens us up to a place where we can start really playing with the input values, the input attributes. And instead of just looking at our independently measured geochemistry, we could start doing multi-element proxies. We could start doing molar ratios, things like principal component analysis results, calculated indices, or any other kind of predictive or predicted property of the data. And this one that you're looking at here is a really simple inversion of the aluminium data, or I'm meant to call it aluminum in this country. But essentially, what this is showing, if I can get the color map to kind of behave, what this is showing is a slight enrichment in depleted aluminum, which is actually, or inverted aluminum, which is actually a aluminum depletion at the core of this system. And the reason for that, talking to the geologists at this deposit, is that there is an increase in quartz veining. And so therefore there's a depletion in the quantity of host rock aluminium where there is mineralization. And so we can also run these non-standard variables through driver, and we can be complete cowboys and start looking at them under this configuration here and getting rapid modeling results to try and help us understand their three-dimensional sort of configuration. So here I've created a proxy attribute, the inverse of aluminum, and it's a proxy for quartz veining in this system. And we can see that it also shows a trend that is very similar to the mineralized attributes, the gold and the copper. Next step in the process, which I'm not going to spend much time on because it's pretty run-of-the-mill, we construct this series of anisotropy models and then use that to create block models. We use that to create three-dimensional predictions on a regular grid that enable us to convert this sparse data set into a dense data set. We often end up with a list of block models that's 30, 40, 50 different attributes strong. So this turns into a situation where interrogating these block models becomes a real challenge, and generating value from them is a time-consuming process, especially when you're there trying to understand what cutoff thresholds you should use to generate your wireframe sort of shells. So that's where machine learning comes to the rescue. We utilize this 3D zones and zone anomaly technique, which is this combination of spatial statistics and unsupervised clustering. And so what this ends up doing is it ends up taking this block model and converting it on a sort of, it's looking at it in a locally adaptive way. It takes this block model and it converts it into a three-dimensional wireframe that becomes representative of an anomaly in this data set. So here for gold, we have our gold zone here, and using unsupervised machine learning, we can extract a gold anomaly zone. somewhat unsurprisingly, our copper anomaly zone, which I'm just loading up here. Oh, it's come in brown. It's not very nice. Our copper anomaly zone here has a very strong spatial and chemical correlation with gold. We have some blowout here where we don't have enough samples, but in general, in the well-sampled core of this deposit, we have a strong spatial and chemical correlation between the gold and the copper, as you would expect. The bismuth, on the other hand, which we looked at earlier, shows a very different relationship, where we end up with sort of a crude kind of halo of bismuth, but mostly just erratic sort of blobs if we had these local bismuth highs. But immediately telling us, hey, we don't have a geochemical multi-element, correlation between the bismuth, the gold, and the copper in this deposit. Actually evaluating those relationships, though, is where the system this system shines. And ironically, this part of the system was built well before the rest of it was even constructed. And that's the core of this software, which is to try and understand multi-element geochemistry and zonation surrounding mineral deposits. So we created an overlap feature, and it's basically a Boolean intersection algorithm. If you've ever done any mesh operations, you can take two sort of three-dimensional mesh shapes and extract where the two of them occupy the same space, kind of like a Venn diagram situation. And that's what this does. However, it does it super fast, and it does it in a sort of exponentially, theoretically, what's the word I'm looking for? Combinatorial way. So what I can do here is I can click on any contributing attribute that I'm interested in. And what I'm doing is I'm actually selecting zone objects from this tree on the left-hand side here. So I can click my gold, my copper, potassium, and I'm thinking porphyry system here. So I'm just going to try and evaluate something related to a porphyry system. Potassium, maybe let's have a look at the iron. The challenge is finding them. There's my iron. And you can see as I'm clicking them, the software is giving me all of the theoretically possible ways that those attributes can overlap each other. And it's actually performing the Boolean intersection. It's actually giving us volumes of how those attributes are related to each other. So I could look at my gold zone only, which unsurprisingly is going to be exactly the same as the gold zone that I was looking at. There it is, it's coming in gray. I could also look at how my gold and my copper overlap each other. So this is the intersection between the gold and that copper anomaly that we found. And it gives us this really nice 3D shape that's representative of anomalous gold and copper. But we can keep going. Gold, copper, iron, potassium. And as we add more, the overlaps typically get smaller. However, here is where we have an overlap between gold, copper, iron, and potassium. And I could even add in my inverted aluminium, gold, copper, potassium, inverse aluminium, which remember is a proxy for quartz veining, and potassium. And here it is here. There's our 3D shape representative. Potentially, it's just in my head, but it's representative of a mineralized potassic alteration sort of signature. And this is what geologists are really, really good at, is coming up with ideas, coming up with hypotheses, and then testing them in some kind of reasonable way. And this basically was designed to give your everyday Joe geologist the capacity to access these block modeling tools, come in and then augment the process with some handy machine learning techniques that help you sort of expedite and remove your dependence on a geostatistics expert, and then come to this space where you can start evaluating things to your heart's content. Really powerful for deleterious mapping or checking that you don't have penalty elements enriched within your mineralization zone. I could throw in attributes like arsenic, cadmium, and immediately we can evaluate where they exist. And in this case, I think they have a very small overlap. So let's just have a look at the arsenic, cadmium, potassium zone here. It's only got 6.7 million cubic meters. So we basically have a very small correlation between enhanced arsenic, enhanced cadmium, and enhanced potassium in the system. So good news for the future mine at Saddle North. So I'm going to push on to the second part of this talk, and I realize I rambled a little, but I'm just going to quickly whip through the locally adaptive application of the spherical continuity mapping algorithm. So as I mentioned earlier, we don't have to apply the spherical continuity mapping algorithm to all of the data at once. We can actually apply it on a local moving window. And that's really, really helpful when you're evaluating deposits that have locally changing features. Things like folds are a classic case, but this is an example. This is the Duluth copper nickel sulfide deposit in Minnesota. It's an absolutely enormous deposit. And I've just taken a small zone from this deposit here to give you an example. But basically, this is contact-controlled intrusive, mafic intrusive deposit, and the grade continuity or the directional continuity of grade in this system sort of follows the lower bounding contact, and which is an undulating three-dimensional planar surface feature. So what do you typically do? In a typical sense, you would come into this deposit. Either you have to manually define the folds, the structure related to it, which if you've got a good handle on it is great. It often takes time. If you're trying to deal with fold limbs, you might come in and domain this deposit up into individual limbs of the fold. But in any case, you're going to be coming up with compromises, and you're going to be going through a interpretation or sort of human-led process to construct a reasonable model that is locally adaptive using current techniques. With Driver, however, we can define a series of local overlapping moving windows, which basically are designed to capture a small quantity of data. However, that quantity of data has enough sort of data in it to define a directional trend. We then run our spherical continuity mapping algorithm across each of these local windows in turn. And what this does is it applies the StereoNet ellipsoid extraction tool to each of these local windows, and it's able to define an ellipsoid model related to that kind of micro domain, if you like. We independently measure the strength of directional continuity at each place, at each of those windows. And it's kind of neat. This is an empirical measurement-based approach, which is reproducible. This is not neural network. This is not neural network style stuff. This is basically a style of unsupervised machine learning technique. But essentially, we can tune it slightly to seek different feature scale lengths. However, it's a data-driven method that is derived directly from the drilling data itself. The difference being that you don't have to define any kind of structural plane, you don't have to define any kind of structural zone or any kind of shape or wireframe that actually provides the system with the locally varying anisotropy configuration. This does it all by itself, all on its lonesome. I'm going to skip that demo. I was just going to show you the same thing in the 3D window. Once we have this LVA field, we can downsample or upsample, I guess, the ellipsoid field to the block level. So every single block in the block model gets tagged with its own anisotropy model. And we can then interpolate using a locally adaptive ordinary kriging. So it's just like a normal kriging algorithm, except instead of running the data as a whole, we look at each block in turn, and we can change and modify the search space, the ellipsoid parameters, and the actual weighting on each of the ellipsoid axes for the variogram model on each of these individual blocks, basically controlled by this anisotropy model that we put in here. And so to give you some comparison results of why this is really cool, here is that slice that I was showing you a little earlier. And here's a reasonable approximation of a global variogram and global global interpolation using ordinary kriging across this sort of deposit. And what I've done here is I've basically chosen an ellipsoid that is a compromise. It's mostly biased towards this large area over here. It sort of follows that trend. And we kind of sacrifice a little in this grade inflection where we're changing and going up to this this sort of ramp on the fold axis on the other side of the syncline here. So it's a compromise. It's a good model by all means, but it is of course some kind of compromise. With Driver's automatic method using the locally adaptive approach, we can define this ellipsoid field using the local adaptive machine learning. And then we can apply this on a block by block level and produce a locally adaptive kriging. And there are some really interesting but subtle differences between the results, which I think you'll enjoy. So kind of it's easier to see the comparison, and I promise I'm not crazy. There is a difference here. But the difference really is related to the inflection points where you get the grade changing. So the first difference is that the LVA analysis was able to actually constrain its anisotropy down to a higher aspect ratio, where you had this feature along this wall here, along this along this limb of this fold. And so you get a slightly tighter but more defined grade trend in this area. Here, it kind of goes down in sort of steps going down the side of the fold. The biggest difference is where you have an inflection point in the grade. And here, what's happened in the global one is that it's biased and it's sort of pushed the result down below the grade inflection point. And we've started predicting grade down below here, and we've actually got a gap in the grade continuity across this fold axis. The LVA one is able to adapt to this locally, and it's able to essentially produce a more consistent grade distribution as you change the grade direction. Same again for the other side of the fold axis, you end up getting a slightly tighter and more defined grade trend. This is really significant, and you're probably thinking there's only a couple of blocks that are different, but each of these blocks in this particular model is 160 meters wide. So this is representative of some pretty significant grade continuity that's being maintained or lost in these models, which would have reasonably significant impacts on any kind of pit plan or pit optimization that's run. So I think that takes me to the end of the time here with a few minutes for questions. But just to sort of sum up what we're trying to achieve with this software, we're trying to build automatic pipeline sort of modeling that really enables or acts as a catalyst to start modeling and using all of the data that is typically collected in these deposit data sets. More often than not, we see these data sets where they're assaying for a full, very expensive analytical suite, but never even looking at 80% of the data that's collected. So while I fully admit these are not the most accurate geostatistically perfect models that can be created in the world, there are a lot of compromises that go along with automation in this process. The purpose is to try and act as a catalyst to create the models, to start creating something that basically using all of this information and estimating it into block models, the richness of the interrogation process, once you have all of that data in a full three-dimensional sense, is really invaluable. So our anisotropy method is designed to sort of help a user understand the modeling parameters, understand the anisotropy to a reasonably high degree of accuracy, which in some cases can actually improve, I think, the quality of the estimation at the end of the day, especially if time and effort end up causing you to make sort of sacrifices on the models that you've created. I'm talking for those locally varying cases. And yeah, these are hopefully really important innovation steps that are needed to move towards an automatic modeling world. A lot of the companies out there are trying to set off programs or support programs to advance automatic modeling solutions for project evaluation and continual updating of their resources. And that's where we're trying to position Driver as software that can hopefully become a key part of that automation trend. So thank you very much. Yeah, any questions? I'm happy to delve into it.
Thank you, Alex. Very interesting. Let's open the floor for the questions if anybody has any questions.
Hi, Alex. It's Mark Noppe. We met at PDAC. Clinton introduced us and you took me through some of this.
Oh, great.
Yeah, good to see you again. I guess just one observation. I definitely like the local continuity analysis and the representations of continuity. I think that visual and ability to display it and identify it, and then also that combined attribute correlation continuity shapes in terms of you showed me that before. I think that's very powerful in terms of understanding the complexity and interactions. The question I have is when you showed what you called the block models, the closer spaced representation of the data, a question I have is, do you have the ability to run multiple realizations similar to a conditional simulation on that? Because obviously you've generated one version of the truth, which is obviously, should be the most likely, but is there the possibility of running ranges and looking at extremes?
That's next steps. Absolutely. That's I think that's the the natural next the next sort of step. We've been focusing a lot on we've actually sort of stalled a lot of the R&D over the last sort of 9 months to get the product out there and start building a customer base, a user base, to start collecting feedback on it. And you're absolutely bang on. That's one of the key next steps that we're looking to follow, especially with the support of the cloud infrastructure. I think we should be able to do a hell of a lot of damage on that world. Yeah.
Thanks, Gary. Oh, thanks, Alex. It's Paul Gow here. This is a nice example. You often hear people talk about machine learning and et cetera, taking away work from geologists, et cetera. But this is a great idea, great example where it's actually providing, some tools for geologists to think about all the different aspects. I guess you've focused primarily and understandably on copper and gold, and you looked at the aluminium, et cetera here. What do you see as the best way to sort of be doing, with those 40 element data sets, doing the sort of exploratory data analysis in those little known elements, et cetera, through this platform?
Yeah, I mean, that's a tough question in the sense that it's very different for the deposit that you're working in, and your knowledge of the deposit and sort of where your understanding of the deposit lies. And one of our biggest challenges, which was a little bit of a curveball and a bit of a surprise for me, is generating all of this information and then helping people to sort of use it, helping people to come up with multi-element proxies, because I think there's a real tendency, and probably rightly so, there's right hesitant to create something just for the fun of creating it, especially when there's a sort of deficit involved in how much time it creates to invest in it and go and work on this sort of stuff. So, the idea of just trying it is sometimes challenging to encourage people to do. But once you sit in front of it and you've got this information and you start clicking, you start understanding, and you start seeing how things are related to each other in this sort of very dynamic and flexible environment, people end up coming up with some really neat sort of conclusions. And often they relate around mineral assemblages. They look at the contributing components to a certain mineral species, and they're able to come up with an independent proxy that they can then use to, maybe, look back on the geologist logs. Hey, was I logging stibnite in this thing? And you can actually look at some of the contributing, sulfides into that and understand whether you were indeed, correct in the observation that there was that sulfide species. Lithological proxies in general are another way to start beginning the analysis and taking a look at some of the host rocks. I've got this package here, I've got this intrusive group here, I've got this mafic assemblage, that looks like they're barren dikes that are intruding into my deposit. And just looking at some of the basic geochemistry pathfinders that follow those, you can look at phosphorus, titanium, magnesium, a combination of those three, or even elevated iron, will usually nail down an intrusive basaltic dike in your system. And, even though that may be something that the geologists have logged really, really nicely, having a completely independent geochemistry-driven proxy for that dike, it's a really nice, it's a really easy, quick way to sort of evaluate where it is. And one early project we were working on, we used Driver for exactly that. We used it to nail down, they had this absolute dog's breakfast of a shear zone with different sort of, with a sort of different assemblage, a whole lot of different assemblages in there. And we found a series of mafic dikes that were cross-cutting that they hadn't actually registered in the lithological logs. And so this is just a really easy way, quick way to identify them. Yeah.
Any more questions in the audience? We have 4 questions online. You may be able to see them, but I can read them for the people too. Although you're running out of time. One is from Malcolm Power. He is asking, can one progressively add infill drilling to evolve the ore body models as more data is available potentially in specific areas as the mining area is approaching it during the mine?
Yeah, absolutely. We basically set the system up in a way where you can, where it's just like Leapfrog or something like that, where every object has its dependency, it has its history, it's got its parent, its grandchildren, and its children. And so what that means is that we can have remodeling without loss of any kind of user input. So you can update your drilling data set, and it will just recalculate everything. It'll just send all the jobs back to the cloud, recalculate, update. And the anisotropy models will change with more data. Hopefully they don't change too dramatically, but as you build more information in there, you end up getting a tighter convergence towards a certain situation. So yeah, it's really interesting to actually watch it updating. The next question was, has or can this be trialed on large waste rock dumps? Yeah, I've tried it once on a waste rock data set, on a tailings pile, not a waste rock pile actually, but it was tailings, and the results were overwhelmingly horizontal. It picked up a whole lot of horizontal stratigraphy in the data. Maybe it wasn't the greatest data set, but I think it would be a really interesting application of it for sure. One of the downsides, the blatant downsides to this style of analysis is, and it's one of its upsides and downsides, it's one of those catch-22 situations. It needs a lot of data to function. The algorithms will see what they see. And if the trends and information are not encapsulated in the data because you do not have enough data, then they won't perform in a reasonable way. It's also something that's hard to quantify, and it's hard to exactly put a hard cap on, is there enough data, is there not enough data? And so we're constantly working on ways to sort of qualify data sets. However, in general, the rule of thumb is that you need a reasonable resource sort of estimation quality data distribution. So you need to be getting towards that first sort of resource estimation. Once you start getting to the point where you can make a block level prediction, you have enough data for that anisotropy algorithm to run. And then Grant Valentine.
Yeah.
Can it take geometallurgical values such as recovery and throughput? Can it convert those into economic evaluation of the blocks? So it can take anything. It can take whatever you put into it, and it will run exactly the same procedure on it. There are some considerations that need to be made. If you start slamming elements or contributing elements together that may not have the same geostatistical dependency on each other. So it's often a good idea to run the contributing, so say you've got a proxy for recovery through the geochemistry. It's often a good idea to run the independently measured attributes in their own analysis space and then calculate that proxy for recovery off the block model itself at the end of the day, rather than do that calculation off the drilling data, because ultimately it's going to use those independent attributes to form the prediction of grade distribution. So there's different ways to do it, but absolutely, and we're really trying to encourage that move into that sphere of basically modeling non-standard stuff. Or stuff that isn't typically modeled very often and routine, and that's kind of the beauty of sort of unlocking an automatic method which is able to achieve this, is that you're not really constrained by the time or the cost. I think there's another one here.
Yes,
is it possible, Mark Simpson, is it possible to constrain the analysis within hard domains, for example, lithological wireframes or fault surfaces? Yes, absolutely. So a user can, we're not the most advanced software in terms of creating those lithological domains in the first instance. I'd highly encourage you to turn to something, like Leapfrog, Vulkan, Micromind for creating those 3D shapes. However, you can upload absolutely anything into the driver system. You upload it as a wireframe mesh, and then you divide the deposit analysis into those individual domains, and you're able to come in and basically what it does is it segregates things down, and you can run each of these wireframe domains in a single space. So, yes.
Yeah, also Greg is asking for your contact details. We will share with him.
Yeah,
Next week we will have Professor Charlotte Allen. She is the director of QUT Central Analytical Research Facility, and we hope to see you next week. And thank you again for presenting for us today. If you guys, everybody can help me to thank Dr. Alexander Wilson again, please.
Thank you so much. It was a real pleasure. It is snowing here, so I'm gonna I'm gonna go and start the fire. All right. Have a good night, everyone. Thanks a lot.
Thank you.